Prove the theorem that states that the angle between the tangent and the chord drawn from the point of contact is equal to the angle in the alternate segment. Alright. Okay, so in today's video we're going to prove the very famous tan chord theorem. Right. Let's see how well can I reproduce this sketch. Right, matriculants, please bear in mind that in your exams you are going to be given a diagram to work off, and so thus your labels will be based off that given diagram. Okay, in this video I am going to construct everything from scratch by myself. Right. Okay, so obviously the first thing you need is a circle. Okay, let's look at some keywords inside the statement, right? One statement that we have is this word tangent. We also have chord, and then we have angle between the tangent and the chord, right? And we're going to need an angle in the alternate segment, right? So in other words, the opposite segment. Okay. Alright, so those are my key terms. Right, so I'm going to then try to create a drawing. Okay, right, so first thing I need is, very importantly, this is a tan chord theorem, so I need a tangent. Okay, there's my tangent, there's my point of contact. Okay, right, so I'm going to label this tangent E D F. Yeah, those are random letters, but anyway, EDF, I'm going to have a center. I've drawn my tangent quite skewed, so the center is going to have to be somewhere over there. Okay, so center O. Right, so okay, this that I've now drawn now would be given information. Right, so given center, not center, circle, center O. Right, with tangent EDF, and let's actually also give a chord, right? So since we need a chord, right, and chord PB, right? So let's just put a chord in here. Maybe, how would we need this chord? Okay, so we need an angle between the tangent and the chord. Right, so our chord has to be not PD, but rather DP. Okay, right, so some chord over there. All right, some chord over here. Okay. Maybe something else that should be given is the angle in the alternate segment. Oh gosh. Wow. Okay, so let's call this point A. Okay, right, so also given, we will say okay, let's just read circle center O with tangent EDF and chord DB, where D is the point of contact, between the tangent and chord DB, right? Let's do that with A on the major segment of chord. This time we can say chord because it's actually drawn, chord DB, and C on the minor segment of chord DB. Okay, so I'm going to draw in another point over here, point C. Okay, so then we'll be required to prove that angle BDF, right? So this angle over here, I have to prove that that equals to angle A. Okay, I'm going to remove that because we haven't proved it yet. Okay, right, so if to prove that that's equals to angle A, and we have to prove that angle E DB. Okay, so this angle over here, so this one here. Okay, so that's the tangent, that's our chord DB, right? That's the angle between the tangent and the chord. That has to equal angle C. Like that. Okay, right, so we've now set up everything. This must equal angle C. Okay, so that's our point of contact. EDB, that must equal angle C. Okay, so let's start off with this first part of proving that angle BDF is equals to angle A. Okay. Right, so again, these proofs always come down to some sort of a construction of radii. Okay, so we're going to go construction, right, and we are going to draw the diameter of the circle. So diameter, which letter don't we have here? Let's say PD, okay, and then we are going to join PB, right, and then after that we're going to let angle BDF, right, so this angle that we are working with, angle BDF, we're going to let that equal angle D2, right, and we are going to let angle PDB to equal angle D1. Okay, so let me just put in all of that so you can see what I'm talking about. Okay, so we're going to have the diameter Okay, so what we have is this diameter PD, right? And we've joined PA, right? And we are letting angle BDF, right? So we're letting this angle equal angle D2, right? And angle PDB, this angle over here, right? We are making that one equal angle D1. Okay, so that's all the construction that we've now made, right? And our diagram is now set up for us to do our proof. Okay, so we'll go into the proof. Alright, so with the tan chord theorem, right, there is 3 things that you need to find that are equals to 90 degrees. Okay, obviously the first thing that's the easiest to do is the fact that angle D1 plus angle D2 is equals to 90 degrees, right? And that's because a tangent is always perpendicular to the radius. In this case, we're going to write diameter because we've drawn a diameter PD. Okay, so diameter, right? Let's find something else that's 90 degrees. Well, in the triangle PDB, okay, if PD is the diameter, then angle B, in other words, angle PBD, right, that angle inside of it there, let's draw it. That is a 90 degree angle. Right. Let's give it a nice highlight. Right. And I'm not going to do this one because, yeah. Well, I can. Let's do it. Just to remind us of these two. That's why I didn't want to. No, I'm not going to do it. It's going to get clustered. Okay. Alright, so let's go back to here. Angle PBD, that's equals to 90 degrees. That's because that's an angle in a semicircle. Okay, and then what else do we have that's 90 degrees? Remember, there's always 3 things, so we need a third one. That's going to be inside this triangle PDB. You already have a 90 degrees, so angle P plus angle D1, right? So angle D1 plus angle P, right? Those two will be 90 degrees. Okay, so this angle and that angle must be 90 degrees because you already have a 90 degrees. So sum of angle of triangles will be 90 plus 90 is 180. Okay, and the reason for that is exactly that. Sum of angles of triangle. Let me write over here. Triangle PBD. Okay, so now we have our 3 things that are equal to 90 degrees. Once you have that, okay, there's some sort of a relationship that's going to happen over here. Right, so notice that you have a D1 over here, you have a D1 over here. I'm looking at this and this. Okay, that's what I'm looking at. Okay, so I have a D1, I have a D1, I have a 90, I have a 90. Okay, so the only thing that's different is this D2 and this P. Okay, you have D1 on both sides and both of them end up being equal to 90. Therefore, angle D2 must equal angle P. Okay, that comes just from the logic of those two statements. Okay. Alright, so now once we have that, we see that angle P, right, so we can write this, but, okay, angle P is equals to angle A, and those are angles in the same segment I always like to add subtended by arc. What are they subtended by? Arc dB. Okay, it's not necessary, but I always just like to add it, right? So what we have now is that this angle P, okay, it's too big of a highlight. Okay, now what we have is that this angle P is equals to this angle A. Right, and that's just from theory. Okay, let's put a stripe on it. Okay. Right, so what do we have so far? Right, so we have angle D2 is equals to angle P. We have angle P is equals to angle A. Right, those two things are equal to angle P. So then therefore, angle A is equals to angle D2. Reason is they are both equal to angle P. Right. Okay, so did we call angle D2 anything? Yes, we called angle D2. Remember over here, we called angle D2. That was originally angle BDF. Okay, so that means that therefore angle BDF is equals to angle A, right? So that means that we have now proved this first statement over here. Okay, so we've got this first part done. Alright, so now let's go for this second part where we need angle EDB. Okay, let's just highlight it. It's quite hard to see it. I'll do it in orange. Okay, orange doesn't want to select. Okay, there we go. Right, so I'm talking about this angle. Okay. That's okay, so we're talking about that angle between the tangent EDF and this chord DB, right? So that big angle. We have to prove that that is equals to angle C. Alright, so the first thing I can see is that by construction, angle A, no, can't start with that. Okay, so by construction, A, B, C, D is a cyclic quadrilateral. Okay, that's by construction. Right, so this figure A, B, C, D, that's a cyclic quadrilateral because all the vertices are on the circumference of the circle. Okay, so that means that angle A, right, plus angle C is equals to 180 degrees. These are opposite angles of cyclic quad. Okay, and then also over here a tangent is a straight line, so angle EDB plus angle D2, right, must also equal 180 degrees. Let's just move down a little bit. Reason for this is angles on a straight line. I'm going to name it EDF. Okay. Right, so what do we have? Notice over here that angle A is equals to angle D2. Okay, so we can write but okay, angle A is equals to angle D2, and we proved this above. Okay, so which means that over here this D2 is actually an angle A, right? So with the same reasoning as what we did when we were looking at this section over here, where we had a D1 and a D1, a 90 degrees and 90 degrees, and two things that were different. So in order for those two equations to be true, it means that those two angles have to be equal to each other, so that both the statements equal 90. With the same reasoning, looking at this and looking at this, noting that this D2 is actually an A, right? Then you have A is equals to A. You have 180 degrees is equals to 180 degrees. So then therefore, right, C must equal this big angle. EDB must equal angle C. Okay, is that what we had to prove? Yes, fantastic. That is what we had to prove. Okay, so there you go. That is one form of the proof of the tan-chord theorem. If you do find any other proof, you are more than welcome to use it, right?